Welcome to the last lecture of the class, where we are going to do our final review for the exam on earth science and astronomy. So we started with earth science. We learned about rocks, and it's very interesting to note that four elements, iron, oxygen, silicon, and magnesium, make up almost 93% of the Earth's mass. And an additional four, nickel, calcium, aluminum, and sodium, are another roughly 5.5%, leaving only 2% of the elements outside of those eight. So those are by far the most common elements of the Earth's mass. Now, because of differentiation is more dense things sink, less dense things float. And so the Earth has gone through differentiation since its original formation. And we have 1 or 3/4 of the crustal mass is just oxygen and silicon, and only 5% of the crust is oxygen or is iron, whereas the core is largely iron because of its high density. Oxygen and silicon combine to give us silicon dioxide, which is the basis for most of our rocks. So we call this silica. So minerals are naturally formed inorganic. So organic was copper-based compounds. So inorganic is not copper-based, not carbon-based. Crystalline solids. Crystalline means that you have a repeatable structure. So this position, go over X amount, and you have another atom, go over this amount, and you have another atom. That's what crystalline means. So we identify crystals by their form, hardness, cleavage, fracture, color, density, things that are physical properties. So hardness, you should know that tin on the Mohs hardness scale is the hardest, and diamond is a 10. And if you try to rub two things on each other, the harder one will scratch the softer one. So that's how you can tell hardness. Crystalline form is actually related to cleavage, or cleavage more accurately is related to crystalline form. If you hit a crystal, you can get it to cleave or to break along a face on the crystal structure. And so that's what cleavage is. Fracture is the opposite of cleavage. If you hit it, it just breaks into shards rather than breaking along a plane. Color is pretty obvious, and density we've already talked about. So silicates, things made out of silica, are the majority of our rocks. Non-silicates, things like carbonates, like calcium carbonate, that would be limestone, or sulfides. Some of the prettiest things out there are the sulfides, oxides, halides, phosphates, and native elements. So you should have some understanding of what these different minerals are. When things cool, if they cool slowly, then the crystals will grow large. If they cool quickly, you don't have much crystals formed. So something that cools very quickly is obsidian. Very rapid freezing. So no crystals. So obsidian is glassy, it has no crystals. And something that is very slow to freeze is granite. So granite has fairly large crystals, different minerals, so you have different types of crystals. Things with a higher silicate content freeze at lower temperature. So as you're cooling, the things that freeze first are the things that don't have much silicate content. And the last things to freeze, because they freeze at the lowest temperature, are the things with high silicate content. So we had a homework problem where you actually had to determine that. You had to calculate how much silicate content you had in different materials, so you could rank them based on their silicate content, which one was going to freeze first. You can also have crystals form in water where you have precipitation and evaporites. Rock types, igneous rocks are molten rock that freezes. And remember, magma is below the surface, So here's the surface of the Earth. Magma is molten rock below the surface, and above the surface it's called lava. So there is no fundamental difference in what the contents are of magma and lava. It's simply where you find them. So igneous rocks, things that were melted and froze. So basalt, andesite, granite, obsidian, tuff. These are all examples of igneous rocks. Sedimentary rocks are rocks that were eroded and deposited. Actually, I should have started with weathered first. Weathered is you take a rock and you break it apart. So when you walk on rocks, you will be weathering those rocks. And then erosion is moving them. So obviously, if you're walking on a path, you will cause some erosion because you'll cause some movement of the material. Oftentimes, water and wind are the two predominant erosional vectors. Weathering, as the name implies, is often caused by weathering, things like freeze-thaw cycles. You may have noticed in Lincoln, usually our roads are really bad this time of year. Why? Because water gets in cracks and freezes. And when it freezes, it expands and it breaks the rock. And then it thaws and washes rock out, freezes again, breaks it more. And so that's why we get those big old potholes every year, is the freeze-thaw cycles. If it would just freeze once and stay frozen all winter and then thaw, we wouldn't have such a big problem. And finally, metamorphic rock. Metamorphic rock, it could have been igneous or sedimentary rock that has been heated, pressurized, or chemically altered. So metamorphic rock is rock that has been altered. So you might have some calcite, and it's put under high pressure and temperature, so it flows a little, and you get these swirly patterns in it. And then that's a metamorphic rock that we call marble. So metamorphic rock could have been either igneous or sedimentary rock that has been changed by the environment through heating or pressure, probably both. Can be some chemical elements as well. Volcanoes. Most of what we think of as volcanoes are things like this that are the cinder cones. These occur when you have a violent eruption, and then a lot of stuff falls nearby and less stuff falls farther away, and it creates the cinder cone. So cinder cones have violent eruptions. They tend to be magma that does not flow as easily, so it builds up higher pressures. Shield volcanoes are the kind that they have the Hawaiian Islands. Shield volcanoes are more like this. They're called shield because they kind of have the shape of a shield. And the magma just comes out and flows downhill. And so in Hawaii, when they have volcano eruptions, they have magma that just will flow down the hill. It'll flow through. You might remember maybe 3 years ago when there was a volcanic flow that wiped out a huge part of an island, filled in a bay. It was pretty incredible. And so shield volcanoes are a different kind of magma. And these shield volcanoes often occur over hot spots. So Hawaii, you have the crust of the earth, and then from the mantle, you have a hot spot that has come up and punched a hole through and makes the volcanoes. But because of plate tectonics, we're going to have motion of that crust over this hot spot. And so what happens over time is you have older volcanoes out here, and they're getting younger and younger as we get closer to where the hot spot is. So the hot spot used to be at this part of the crust used to be over the hot spot maybe 10,000 years ago, and so that's where the volcano was. So the Hawaiian Islands are part of a chain of islands that stretch all the way down to Tonga that were created from one hot spot that kept punching through the crust at different locations as the crust slid over it. And composite volcanoes are just magnets in between that have somewhat of both. So I've already talked about weathering, erosion. deposition, I didn't spend a lot of time out. If you have a stream, a lot of time on, you have a stream flowing, the faster the flow is, the bigger the particles it can hold. And when it slows down, it drops them out. So the deposition is when the water slows down, it drops the load of sediment that it was carrying, and then it forms layers, and those layers are what form the sedimentary rock. Now, sedimentary rocks are classified by grain size. So really small is a clay, and then you get larger. You have silt and sand. And then you have, as those compress, they'll form rock. And so the clay will form mudstone. If you have clay and silt mixed together, then we call it shale. And then sand forms, of course, sandstone. And it's in these sedimentary rocks where we find fossils, because we have animals or plants that died and were buried before they could decompose. It's really important that they're buried before they could decompose. If they decompose first, you don't have anything to preserve. And so that's how fossils are laid down, is when you have something that dies, gets buried, and sealed in place. The rock, I didn't really talk about these. I'm just going to pass them by. How do we know anything about the interior of the Earth? It comes from seismic waves. Seismic waves, we have the surface waves, the love waves that are jiggy-jaggy back and forth, and the rotary waves that are rolling waves. And maybe I should make the love waves look like this for jiggy-jaggy. I don't know, same difference. Those surface waves are what we feel, but the ones that go through the bulk of the Earth are P waves and S waves. P can stand for either primary, because it's the first, or pressure, because it's a longitudinal wave. S could stand for either secondary, because it's slower, so it's the second one that you get, or it can stand for shear, because it's a transverse wave. And so transverse waves cannot go through liquid. And so in observing the waves, it was observed that there was a shadow region with no waves, and then only P waves here, so no S waves. So no S waves means that it had to have been going through liquid. This shadow region with no waves at all meant that you had a significant change in wave speed. And so based on the path of these P and S waves before we had the shadow zone, scientists were able to determine the size of this liquid region. Liquid because it had no S waves going through it. And then based on things that came from this, they were able to determine that there was an inner core that's solid. And so while no one has been to the core of the Earth, no one has, confirmed its existence in person, we have evidence from waves going through the Earth that tell us what's inside. So if we look at this picture on the right, it's a really useful picture, actually. We have the outermost part of the Earth is the crust. And the crust, we have the two types of crust. We have the oceanic crust, which might be 7 to 10 kilometers thick. And we have the continental crust, which is up to 30, maybe even 50 kilometers thick. The continental crust is less dense, and so it's going to be bigger. It extends down farther below and up above, and it's just floating on the mantle. Now, the mantle is broken into an upper and lower mantle, and this dividing line here is where the end of asthenosphere is. The asthenosphere is this region in here that the upper mantle and crust, what we call the lithosphere, slide over. And the asthenosphere is like that little grease spot. Now, this stuff here, it's, quote, solid, but it's kind of a squishy solid because it's under high pressure and it's high temperature. You get down to the outer core, the temperature has gotten so hot that it's molten. You get to the inner core, and the pressure is so high that it forces it to be solid, even though the inner core is hotter than the outer core. Now, why is it hot in there? two reasons. Reason number one is during formations, everything fell in. You had energy that went from gravitational energy into thermal energy, making things hot. Reason number two is radioactive decay. Radioactive decay releases energy and makes things hot. So, given time, eventually the Earth's interior will freeze. And in fact, there's evidence that Mars's interior has already frozen. So it will eventually freeze, but not yet. And down at the bottom, it shows us the speeds of waves. And you can see a big, distinct change in the speed of the P wave when you get to the liquid, which is why you have this shadow region, because the speed changed dramatically. And then you see the S wave just disappears when you get to the liquid core, because it's liquid and you can't support a shear wave in a liquid. So Alfred Wegener, and I'm pretty sure I misspelled Wegener, I do every time. I believe I believe this because when I was grading the potential test questions, Annabelle spelled it that way, and I was like, well, that's not right. And I looked up, and it was right. So Alfred Wegener was the one who came up with the idea of plate tectonics. He looked at the shapes of the continents, and you have Africa, and you have South America, and they would fit together. And then looking at fossils, the fossils here and the fossils here match up, and looking at the layers, they match up. And he's like, it looks like those used to be in contact, and now they have moved apart. So he suggested that we have pieces of the crust that are sliding around. And looking at paleomagnetism, that is looking at magnetic fields that are stored in the rock, frozen in rock from when it solidified. And fossil records, there is strong support for this plate tectonics. So we believe that that's what actually happened. And now as we look at the ocean, we see that the ocean has rift zones where magma from the deep comes up and goes sideways and pushes the crust apart, and new crust forms here as the magma comes up. So you have these mid-ocean rises and rift zones where new ocean floor is created, and the ocean floor is pushed away from the centers of the ocean. So that's a divergent boundary in the middle of the ocean where you have these rift zones. But then at the edges, we have the continent. And remember, the continent is less dense and thicker, and this more dense ocean crust, then when it comes to the continental crust, it slides underneath, what we call subduction. And as it subducts, it grinds, melts material, and so we get big magma chambers that float up and create volcanoes. And we get an ocean trench there where it's slid underneath. Now, transform boundaries are where you have the plates sliding anti-parallel to each other. And you're going to have earthquakes and volcanoes in either divergent or convergent, but not with transform, because they're just sliding past each other, not nearly as much friction and whatnot. Further evidence of plate tectonics, we have things like folds. Where I am right now in Colorado, we have the Rocky Mountains. Those are an extreme example of the Earth folding under the compression that was caused by the convergent boundary when the North American plate had the Pacific plate sliding underneath. Now, right now, we have the North American plate and the Pacific plate are transform boundary. But it used to be a convergent boundary. We are pretty certain by looking at the features, that ring of fire. Faults are cracks in a plate. So we have like 8 major plates and a number of smaller plates. And then within those plates, you have faults or cracks in the plate that are caused by the stresses associated with plate motion. Now, the Earth's surface is largely dominated by water. And so 71% of the Earth is covered with water, mostly oceans, right? 97% of Earth's water is in oceans. So the vast preponderance of our water is in oceans. And of the remaining 3%, 2% of the remaining 3% of the Earth's water is frozen in ice caps and glaciers. So it's not really available to us for drinking water or swimming pools or anything. And so if we only have 1.5% of the remaining, or excuse me, surface water, lakes, streams, etc., is only 1.5% of the remaining. And of course, my math here doesn't work out. Actually, it does. There's 1% that remains. 97 plus 2 is 99. 1% remains, and only 1.5% is above ground. The other 98.5% of this 1% is below ground. So surface water is water above the surface of the earth. Groundwater is water in the ground. Now, the hydrologic cycle is the cycle of water's motion. We have heat makes water evaporate. And so the water from an ocean or lake evaporates and goes up. And then, of course, we form clouds. It precipitates, it rains. And then that rain can either go into the ground, which we call an infiltrate, or it can stay on top of the ground and run off. And so that's the hydrologic cycle, the cycle through which water goes. And so up here at 9,400 feet elevation, we have water because it rains very rarely. And so water from the oceans goes up in the sky, moves over us, drops down on us, gives us water. So talking about groundwater, water is stored in porous regions. That's regions where you have gaps between the grains of the earth. And so those gaps then can be filled in with water. And so porosity is a measurement of the percentage of open space in soil. The higher the porosity, the more water you can put into it. Permeability is a measurement of how easily you can push water through. And so you might imagine something that has holes like this. Well, you simply cannot force water to flow through here, even though it has pores, so it has porosity. It has no permeability because the water can't get from here to there or from there to there. So permeability is about the connectedness of the holes. So in my picture up above, water could flow through like that, and so it was permeable and porous. If it's permeable and porous, then it is a place where you can store water. And so we call aquifers the places where you store water. Now, in the soil, if this red line is the surface of the earth, we have down here the water table. Below, it's saturated. Saturated means the pores are completely filled. Up above, it's unsaturated. So if you dig down, initially you're going to be in unsaturated soil. There's still moisture in it. There's still groundwater, but there could be more. So if you had a hose and you turned it on, you fill it with water, it would slowly be absorbed into the soil. Whereas if you dig down into the saturated zone, then water will fill the hole because it's holding as much moisture as it can. So if you drill a well, you want to drill that well down into the saturated soil. So if the water table drops, you're still above the water table. Artesian wells and springs, you have an artesian spring if you just have water coming up out of the ground. And what that means is the water table is above the surface of the ground. You apparently had a non-permeable layer, non-permeable, keep telling it, there we go, a non-permeable layer up here, so the water is stuck underneath, but if you punch a hole through, if your water table is up here, then when you punch a hole through, the water is just going to flow up out of it. So that's what an artesian spring is. Artesian wells are, the water table is not as high, I think, so you have water there, but it's not, pouring out. And hydraulic head is just based on elevational differences, how much pressure you built up. So remember, we learned delta P is equal to rho G H. So you have pressure difference because of the difference in elevation. That's what gives you your hydraulic head. And so that's how you get water pressure down there. So aquifers are regions where you have saturated soil. And I showed you in lecture, like the Ogallala Aquifer. It's just huge water under pretty much the entire state of Nebraska. You can also have a perched water table, which is where you have underground, and then you have an impermeable membrane here. And so water can't go through that. And what you have is then water will form a little perched layer here. So if I live up above, I might drill a well here. That's all fine and good until we go into a period of drought and that water table just disappears completely. So, having a well going to a perched water table is not your best bet. There are some problems that occur with water. Subsidence. I showed you the picture in the Central Valley of California where the soil, the ground level has dropped considerably because they have pumped water out of the aquifer. Well, the water helped to support these particles so they weren't smashed as tightly as they could be. You take out the water, they compress down so the porosity drops when you pump out the water. But as that porosity drops, then the soil is compacted, and so the soil level drops. And that's pretty irreversible. So that's a bad thing. And then we can have carbonate dissolution. So carbonates, calcium carbonate. That's not okay. Calcium carbonate is water soluble. And so as water flows through calcium carbonate, then it will dissolve that and create cavities or holes, things that we call caverns and caves. And if the ground falls into one of those, then we have a sinkhole. So those are problems that can occur because of groundwater. The Earth's surface is largely controlled by streams. So we talked about erosion. Erosion occurs where we have faster moving water. So if I have a stream that's going around a bend like this, the water is going to move faster on the outside, and so it's going to erode away. So this stream is going to, over time, erode out this way. But the water is going slower on the inside, and so it's going to deposit on the inside. And so over time, this is going to be a steeper curve because of the erosion occurring where the water goes faster. And so what this does is it starts to flatten out regions where the water is flowing, because your stream will bend left and right, and as it does, it erodes the material away, deposits new material that tends to be flatter, and so you create these big flat valleys that we call meander valleys. And if this thing gets too curvy, so if it's going like this, and then you have a flood time, that high flow rate will just punch right through. It will form a new path. Well, what happens to this part out here? Well, it gets isolated, and it forms an oxbow lake, named for the shape. So floodplains are regions where a stream has created a meander valley, and when you have high flow, the whole valley will flood. They're great for agriculture because you have very fertile soil that's been brought by all of this deposition with organic matter. But in times of flooding or higher than normal runoff, then you're going to have it flood, and well, that's not good for agriculture. The continental divide is the place that separates the waters from what drains into the Pacific Ocean and what drains into the Atlantic Ocean. And it's on the Rockies here, so it's really close to where I am. Let's skip point bars. Deltas is when a river runs into an ocean. And so you have the river that was flowing like this, and you have the ocean here, and the speed of the water drops dramatically, and so it drops sediment. And the sediment tends to form something that looks kind of like this, and that's the Greek letter delta, and so that's why it has the name delta. So it's sediment that builds up in the still water because of the stream flowing in, carrying its sediment load, and then slowing down and dropping. Now, water will create V-shaped valleys. So if you look at the profile of the Grand Canyon, it's kind of a V shape. because the water has carved it down that way. On the other hand, if you have something that looks U-shaped, so this is water, if it looks U-shaped, which is what Yosemite Valley looks like, then that is the sign of glacier activity. Glaciers are flowing ice. And it's a glacier if it, well, I say flowing ice. Some glaciers don't flow. Some glaciers are alpine glaciers that just sit in place. But it's a glacier if the ice does not completely melt every year. And so, like I said, some flow, some do not. They create U-shaped valleys. You have accumulation zones, the places where you have more ice forming than you have evaporating or subliming. You have ablation zones where you have a decrease, where you have more evaporating or subliming than you have being formed. Moraine is ground up rock that's carried by the glacier. You have side moraines. So if I have a glacier that's flowing like this, the side moraines are here on the side. You have the terminal moraine, which is the material that's pushed ahead in front of it. And then if you have two glaciers that meet, so if I had a measured glacier that met up with this one, it would have its terminal moraine or its side moraine here, but then this here would now be in the center because it's where the two side moraines have formed and it's no longer a side. Final thing we talked about was sand dunes. Sand dunes are formed because you have, once you have a disturbance, as wind blows over it, it picks up here and then it drops off here. And that's how you build up your sand dunes. The sand dune structure is important because geologists use that to explain environments. They look for the structure of a sand dune or the structure of ripple patterns you form underwater to infer then what the environment was for sedimentation. Now, geologic time, of course, this can be controversial in creation versus evolution debates. But there's two ways of dating. Relative dating, this is non-controversial. We all agree in the relative dating. Basically, we have original horizontality. That is that originally all the layers were laid horizontally. We have superposition, which means that the ones on bottom are the oldest and the ones on top are the youngest. Cross-cutting, if I have something that cuts across, actually, let me change that. The thing that cuts across is going to be younger than anything it cuts. So this thing that cut across would be younger than all the layers from here up. That I of course did that wrong. Now that I think about it, it should have been like this. Should have been something that went like this. So it's younger than these layers, but older than the ones that are above it. Faunal succession is talking about the things we find in here. So if we find fossils here, we find fossils here, we find fossils here. The fossils in the younger layers came after the fossils in the older layers. That's something that we all agree on, whether we are creationists or evolutionists. Now, if you are a creationist and you believe in a young Earth, you tend to believe in flood geology, which is lots of water, short time, versus uniformitarianism, which says that what we're seeing has occurred by, what we see in the fossil record is occurring by the same methods we see today. And so it took a very long time to build and little water. Now, when we say little water, we mean a little flowing water. I mean, there's huge oceans that we believe appeared in the past. But the flood, lots of water flowing. The uniformitarianism, everything's occurred very slowly and gradually over time, following the laws of physics and chemistry as we understand them today. Now, what we do not agree, creationists versus evolutionists, is on the radiometric dating and how we get absolute dating for our eras and whatnot. So radiometric dating, you use the radioactive clocks, things like potassium, argon dating, or uranium, lead dating, or of course carbon 14. But carbon 14 is limited; it can't do way more than 50,000 years. And so, for a creationist, 50,000 years is a very relevant time frame. For an evolutionist, that is nothing. The evolutionary, the standard scientific theory says that the Phanerozoic, the that's everything where life exists, is from 543 million years ago to the present. And so 543 million, 50,000 years is nothing. So carbon 14 dating really can't even touch anything useful when you are doing a scientific viewpoint of the age of the Earth. You have to use these other things. Now, carbon 14 dating works on things that used to be living, whereas these here are working on minerals, not things that used to be living. And radiometric dating, it requires that you have consistent half-lives, that you don't have isotopes that have had the half-life change over time. We have every reason to believe that that's a very good assumption. Something that's not as good is knowing what the initial conditions were. So with something like potassium argon dating, they work very carefully to try to find ways to infer what the initial conditions were and not to have to make some assumption of what they were. Now, when we measure the geologic time, it's broken down into eons, eras, periods, subperiods, and epochs. And so the eons, we have the Precambrian and the Phanerozoic. And then the eras, we break down. The Phanerozoic has the Paleozoic or old, the Mesozoic, the middle, and the Cenozoic, the young. The Precambrian time has Hadean, Archean, and Proterozoic. You don't have to pay much attention to that. That goes from 4.5 billion years ago to 543 million years ago. At 543 million years ago, there definitely was life that we see in the fossil record based on the radiometric dating. But at 543 million years ago, or roughly 541 million years ago, there was a great diversification of life, what we call the Cambrian explosion. And so the Paleozoic starts with the Cambrian, and you suddenly have all kinds of life, most of it underwater. And then you go through the Ordovician, the Silurian, Devonian, the Permian and Carbonaceous, is that right? Or Carboniferous? Yeah, Carboniferous. I think I have those in the right order. Then you have the Mesozoic, the middle, which has the Triassic, Jurassic, and Cretaceous. And that's the age of dinosaurs. Dinosaurs ruled the world during that time. Paleozoic, it was fish that primarily were there. And then the Cenozoic, that's where you have the age of mammals. Dinosaurs are reptiles. So you should have some passing knowledge about these. Supercontinents. A lot of people know about Pangaea. Well, Pangaea is just the most recent of our supercontinents, but by following the motion of plates using paleomagnetism and fossils, scientists have put together a number of supercontinents that have existed in the past. And you don't have to know what they are, just know that they existed, what this means, and how they get there. Okay, getting more specific into oceans. Ocean's very near and dear to my heart as a Californian. The water has a high specific heat, so it keeps the coastal temperatures much more moderate. That is, they don't heat up as much, they don't cool down as much. So the temperature does change, but it's not as much as it does inland. I don't know why I guess it's because the atmosphere requires like photosynthesis. That's not a lot to do with the ocean. But photosynthesis, that is a chemical reaction that takes its energy from sunlight and it produces oxygen in the atmosphere from the ozone layer. The atmosphere, we have three atmospheres. The original atmosphere believed to have been largely hydrogen and helium because that was the prominent gases in the solar nebula. And then the Earth doesn't have enough gravity to hold on to hydrogen and helium. They escape. You might ask, well, how come we have hydrogen and helium right now? Well, because of radioactive decay, we're constantly producing hydrogen and helium is the fact. The secondary atmosphere would be things like carbon dioxide and gases that are baked out of the rock. And that would be pretty toxic. The third atmosphere is believed to have come from comets, bringing in water and things that we call volatiles. And that water, as the Earth cooled down enough, it formed liquid water. The liquid water absorbed carbon dioxide and deposited as rock, creating limestone. And so it helped to clear up the atmosphere, and we have our current atmosphere. I'm sure there's a slide coming up with all of that, but just get it out of the way. The ocean, you should know these pieces of the ocean. You have the ocean floor has the abyssal plains, seamounts, little volcanoes, the mid-ocean ridges that I already talked about, the places where we have the rift zones, and ocean trenches, which are at the edges where we have subduction and it creates a trench where it's sliding under. So at the boundary between the continent and the ocean plates, you have the continental rise. Actually, here's the shelf, and then you have the rise and the slope. So you should have some knowledge about those parts of the ocean floor that are occurring where you have the ocean floor subducting under the continent. Waves. I love playing the waves. Waves travel like this. The water molecules do circles as the wave passes. So the water molecules aren't moving with the wave, they're doing these circles. This here is a trough. This here is a crest. As the water gets shallower, it causes friction, which makes it so the water doesn't move as quick, which makes the crests move forward, giving you breakers. And wave refraction is if I have something like this sticking out and the waves come in. So here's my waves coming in. Those waves will bend as they come to that surface. That's the wave refraction. And so these waves, with the motion of the water, they will move sand. So I believe somebody asked, what creates the sandy beaches? Actually, maybe it wasn't your class. It was a different class. Somebody asked what creates the sandy beaches. And it's the water bringing in ground up rock, because that's what sand is, ground up rock. Now, tides is measuring the average height of the ocean. The average height of the ocean moves up and down in response to the gravity of the moon and to a lesser extent the sun. The gravitational force is stronger for things that are closer. So on the side of the Earth where the moon is closest, there's going to be a stronger force in that water than there is on the average of the Earth. And so the water gets pulled away from the Earth and elongates to give you a high tide where the moon is. So if here's the Earth and here's the moon, then you're going to have the water pull out a little, give you a high tide on the side of the moon. But you have the opposite effect on the other side. The water's not being pulled as hard as the Earth, so you have a high tide on the opposite side. So high tides when the moon is overhead, low tides when you're at 90 degrees from where the moon is. So everyone on Earth is going to have 2 high tides and 2 low tides a day. Now the sun also has this effect. So if the sun is here, then the sun will make high and low tides that are the same place as the moon's. And so that would give us the biggest high tides, and that's what we call spring tides. Now, if instead of being this location, the sun was up here, then the sun would be trying to create high tides here and low tides where the moon's high tides are. And so that makes the tides not as big, and so we call those neap tides when it's a 90-degree angle between where the sun is and where the moon is. Atmosphere. The Earth's atmosphere consists of first the troposphere. That's where our weather occurs. So our next chapter after this is weather, and we're going to be focusing on the troposphere. In the troposphere, we have the temperature drops with elevation. And so we have a general cooling as you go up into the troposphere. Then the stratosphere, it starts heating up. And then the mesosphere, it cools again. Then the thermosphere, it gets hot again, hence the name thermosphere. And the atmosphere is 78% nitrogen. Can we breathe nitrogen? Well, sure, it can go in and out of our lungs. What does it do? Well, nothing for the most part. It's that 21% oxygen that's important to us. And then about 0.9% argon. Very trace amounts of anything else. And it's that 21% oxygen that we really like. It's what we live on. Air pressure is due to the weight of the air above. So I am up here at an elevation of almost 10 kilometers. Really? I'm almost at the top of the troposphere. Yeah, that's... So the air here, the air pressure is much lower. And so it's about 70% of the air pressure that you have in Lincoln, and hence I get about 70% as much oxygen as you get in Lincoln, which means that I get short of breath when I'm doing these lectures sometimes just because I'm not getting enough oxygen in. So the actual boundary for the troposphere, it says about 10 kilometers. It's going to vary based on weather conditions and the local geography. The stratosphere is where we have the ozone layer. And we think of the stratosphere as way up there, but of course, if you look at all the rest of this, now exosphere is outside the Earth's atmosphere, generally speaking. But even going up to the end of the thermosphere, that's way out there. And stratosphere is not that high, but it's high compared to the troposphere where the weather occurs. The ionosphere occurs up here in the mesosphere. Ionosphere is where you have ionized gases, and that's where you have things like northern lights. The seasons. The seasons are caused because the Earth is orbiting around the sun in a plane that we call the ecliptic. But the Earth is spinning on its axis, and that axis is tilted about 23.5 degrees from the axis of the Earth's orbit around the sun. And so that means in my position like I've shown here, if you exaggerate the Earth now, the sunlight, here's the Earth's equator based on its rotation, and the sunlight is hitting directly south of the equator. So that would be summer in the southern hemisphere. But up in the northern hemisphere, the sunlight is hitting at a glancing angle, which means we're getting less light. Also, anything that's in this region here, 23.5 degrees from the North Pole, would be not getting any sunlight. And so that's what we call the Arctic. Down here, we have that same this region right here. It's the same 23.5 degrees. The sun isn't setting, and that's the Antarctic. And so that's what defines the Arctic and Antarctic circles, 23.5 degrees from the poles, because during the right time of year, you get full sunlight, never a sunset, or no sunlight, never sunrise. Now, as the Earth goes around, if it comes over and we have the Earth on this side, then we're going to have just the opposite. Now we have direct sunlight in the northern hemisphere, so it's summer in the northern hemisphere, and the Arctic Circle doesn't have the sun set. and the Antarctic Circle doesn't have the sun rise. The tropics are defined as this region 23.5 degrees from the equator, where at some point during the year the sun will be directly overhead. So seasons are caused by the Earth's tilt, not by other things like when the Earth is closest to the sun. The Earth is closest to the sun in early January, which if that's what caused summer, then the whole Earth would have summer in early January. Well, that's not it, right? Solstices and equinoxes. The solstice is when, well, I showed a picture here. This is what we call in the Northern Hemisphere the winter solstice. The solstice is when the sun is at its extreme, either north or south as viewed from Earth. The equinox is the position I didn't show if the Earth was straight in or out of the sun, when the ecliptic is crossing the equator. And so the equinoxes are what start fall and spring. The solstices are what start winter and summer. So we define our seasons based on those. Greenhouse effect, we have that whole lab on the greenhouse effect. So you should know what some of the greenhouse gases are, how the greenhouse effect works, why it's important for us to have life, but why it's bad if we have too much. And now I have a little bit on this about air motion, which leads us into weather. So hot air, if you heat the air, it expands, so it has a lower density. And that lower density makes it so it floats up. And it tends to have a lower pressure. If you cool the air, it condenses, it becomes higher density, and it sinks. Very important for understanding our weather. Notice I put weather continued here. This is the first page of weather, hopefully. Oh, I have these out of order. This one here is supposed to be ahead of the other one. So we need to understand our variables that weather depends on. Humidity, that's how much moisture is in the air. So we have things like grams of H2O per kilogram of air. A concentration, just like what we did in chemistry. Relative humidity is equal to the humidity divided by the saturation humidity. Saturation humidity is what's the total amount of moisture that the air could hold. Hot air can hold much more moisture than cold air can. And so relative humidity is saying, okay, we have this much moisture, this much absolute humidity, but we can hold this much more, and so that's a ratio, and then of course times 100%. Let's get into percent humidity. The dew point is the temperature when saturation humidity would occur. So the dew point is a number that tells you how much moisture there really is in the air. If the dew point is above the current temperature, then you are supersaturated. You have more moisture in the air than the air can hold. If the dew point is below the current temperature, then the air can hold more moisture. And so if the dew point is 40 degrees Fahrenheit, that sets how much moisture is in the air. So the dew point is really more telling than the relative humidity, because the relative humidity, you can have the same moisture in the air. The temperature drops, well, the humidity is going to rise because the air can't hold as much moisture, and the amount of moisture stayed the same. So if you reach 100% humidity, then you're going to have more condensation. You're going to have water droplets form, and that releases heat. So things get hotter when water droplets form. If you're below 100% humidity, then you have evaporation that's more common, and that actually causes cooling. Now, hot air rises because it expands. You heat it, it expands, becomes less dense, and it rises. But as it rises, it expands and it cools. And so you have the dry adiabatic lapse rate that's around 10 degrees Celsius per kilometer rise. Now, moist adiabatic lapse rate, if it's moist air, that is, if you are at 100% humidity, so moist here means 100% humidity, relative humidity, then you're going to be having condensation, which releases heat. So that's only about 6.5 degrees Celsius per kilometer, if I remember correctly. And then the troposphere, the air is actually cooling as you go up by about one of these 6.5 and one is 6. They're very similar, the environmental lapse rate and the moist adiabatic lapse rate. So the warm air will rise, and when you get to the point where you have 100% humidity, then you will form clouds. But if the clouds are still hotter than the air around, they'll continue to rise, and so you'll have a vertical development of the clouds. Once you reach, and we call those more cumulus type clouds, if you reach the same temperature in the air as its surroundings, then the rising stops, and it just spreads out, and that's our stratus clouds. Make sure you can differentiate a cirrus cloud. Those are the wispy ones. A stratus cloud, those are the layered clouds. And a cumulus cloud, those are the vertical clouds. The ones that are rising or dropping. Often the cumulus clouds look like puff balls. Now, the textbook, we had different types of stratus and cumulus, but I'm just focusing on the generalities, except for nimbus. Nimbus means they have water. So cumulonimbus, that's your thunderhead. That's a vertical rising with water. Nimbostratus is a layered. So the nimbostratus gives you rain. The cumulostratus gives you thunder and rain. Okay, we are getting here to the end of our time. The solar system, we talked about the solar system and astronomy. The solar system, you should know all these things that are in the solar system. So make sure that you know the order of the planets from the sun out. Almost certainly I'm going to ask you that. Know which planets are terrestrial. These ones are terrestrial. And know where the gas giants are. These are the gas giants. These ones here, by the way, are called the ice giants. So just in case you're a fan of Thor and whatnot, that's where the ice giants are. Which planets have moons? Everything from Earth out has moons. Earth has one, Mars has two. The rest of them have very large numbers of moons. These are the major moons. So this is the one for Earth. These are the two for Mars. These are the major ones for Jupiter, the major one for Saturn, the major one for Neptune. Asteroids are rocky things out there. The asteroid belt is a belt that falls between the terrestrial and gas giants, and it's believed to have been a failed planet formation that was fractured, probably. There's different theories. Some people say, "Oh no, that's not right." So it's argued. If we go out beyond the planets, then we have the Kuiper Belt, which contains icy objects like Pluto and Quaoar and Eris. And it's where all of our comets, well, half of our comets, let's say, come from. And if we go out further, then we have the Oort cloud. Now, the Oort cloud forms a cloud all the way around the sun that's way out there. And it's the same type of icy objects. So everything in red here is icy, but the Kuiper Belt is in the plane of the solar system, whereas the Oort cloud is all around. And comets are coming from Kuiper Belt or Oort cloud, and they've come too close to something, their orbit has been perturbed, and they come flying in toward the sun. And when they get close to the sun, The sun causes them to sublime, that's basically going straight from solid to gas. And then that gas is blown away by the solar wind of the sun, so it blows away from the sun. And we see the light then scattering off of that gas, and that's what we see as the comet. In observing, okay, so I already talked about this. We don't need to review that. Solar eclipses occur when the shadow of the sun falls on the earth. You have to be just the right spot. Lunar eclipses occur when the shadow of the earth falls on the moon. If it's nighttime and there's a lunar eclipse, you can see it. So we see lunar eclipses regularly. Solar eclipses, you have to be just the right place at the right time. They don't occur every month because the plane of the ecliptic, that is the Earth's orbit around the sun, is tilted about 5 degrees from the moon's orbit around Earth. And so usually the moon is either above or below the straight line connecting the sun with the Earth, and thus we don't get eclipses. But when the moon is crossing over the ecliptic, that's when we get eclipses. So we call it eclipse season, and it turns out we get eclipse season, I think it's about every 13 months. The celestial sphere model is pretending that there is a big sphere that all of the stars are on. The planets are not on that sphere, they're inside of it. But the celestial sphere, we pretend all the stars are on that, and it gives us an easy way to identify where stars will be at a given time. And we identify locations on the celestial sphere by measuring the declination. So the declination is the angle north or south of the celestial equator. And then we measure the right ascension, which is a measurement equivalent to longitude, measuring around perpendicular to the declination. So every location on the celestial sphere has a declination and a right ascension. The Milky Way galaxy is a flat disk, primarily. And so when we look out, everything we see in the sky, with the exception of just the Andromeda galaxy in the northern hemisphere, is within the Milky Way galaxy. And when you look at the disk, you see a bunch of light because that's the combined light from millions of stars in the disk. Okay, that's the end of the lecture. Hope you had a great class.